not forever. Like you said, nobody's ever made you stay. Hey, when we end up in the darkness, you can get me out of this. Let's have your way. Just one night with you, just one kiss so true, just one chance to prove. Just one night with you, just one kiss so true, just one chance to prove, just one chance to prove. Just one night with you, just one kiss so true, just one chance to prove. Just keep telling me.
Promise I won't waste your time. Leave it up to me and I'll blow your mind. I know the moment when you set me free, 'cause I've been through hell and back. This looks like heaven to me. I've seen some lows and highs. We all lose our way more than once or twice. I know how powerful we could be, 'cause I've been through hell and back. This looks like heaven to me. Looks like heaven to me.
All right, I think we can get going here. Sorry for the delay. I'll quickly introduce myself. My name's Tony Gibbs. I'm a data warehousing specialist solution architect here at Amazon Web Services. I'm going to be taking you guys through best practices with Redshift. I've added a little bit of legacy migration twist to it, but if you're not doing a legacy migration, this is fairly generalized, so you'll still get something out of this. So let's just go over the agenda. I'm going to start out by going over architectural concepts. This is just the basics of Redshift, how it works. So for some of you, if you've been using Redshift, this will just be a review. Then I'm going to cover data storage, ingestion, and ELT in Redshift. We're going to then talk about workload management. I'll touch on our new auto WLM that we are rolling out across the fleet actually right now. A little bit on cluster sizing, resizing, our new elastic resize, I'll cover that. Then I'm going to just kind of do a quick summary of some of the tips and tricks and things like that that I've seen on migrations. Give you guys some additional resources. There won't be open Q&A because of the format of this talk, but I will take Q&A out in the hallway afterwards. So if you guys have questions, I'll stand around and answer whatever it is that you have out in the hall. All right. I always like to just kind of see where you guys are at. How many of you here use Redshift today? Okay, reasonable number of you. How many of you are looking at migrating to Redshift because maybe you have some sort of legacy on-premise system? Awesome. Okay, cool. Well, let's start out here with the architectural concepts. Redshift really kind of starts out from Postgres. So if you are familiar with Postgres SQL, you're going to feel right at home with Redshift. It uses almost the exact same SQL syntax. We obviously rewrote the storage engine to be entirely columnar, so we store the data on disk column by column rather than row by row. We also made Redshift MPP. That's massively parallel processing. So that allows Redshift to horizontally scale out up to 128 compute nodes and storing 2 petabytes of raw storage. We added a lot of OLAP functionality as well to Redshift. So these are things like windowing functions, approximate functions, that sort of thing. The types of functions that you use in an analytics data warehouse. We wrapped all of this up in the AWS ecosystem. So it's in tight integration with things like EC2 or S3, IAM, that sort of thing. And it really is this combination of all of these components that make Redshift what it is. We released Redshift on February 2013, on Valentine's Day to be specific. And since that time, we've continued to innovate and add new features. We add these features every 2 weeks typically. So every 2 weeks, there's a maintenance window. We roll out the latest version of Redshift. You have a choice to either use the current version or to lag one version behind if you want to do your own testing and such. So we call that the trailing patch or the current. Redshift, like I mentioned, is a classic MPP architecture. I'm going to start out by explaining this from that green box up there at the top. You can connect to Redshift using JDBC or ODBC drivers, which we supply, or optionally, you can also use the open source Postgres drivers. They still work with Redshift. So if say you have some Python code that you want to connect to Redshift, maybe you're doing some work with R or that sort of thing, you can use the open source Postgres drivers to make those connections and work with those applications. You connect to something that we call the leader node. The leader node really acts as it's a query coordinator. It holds a bunch of metadata. The catalog resides on the leader node. And what'll happen is when a query hits Redshift, that leader node will send the code down to the compute nodes, and every one of those compute nodes will execute that query in parallel. So that's the MPP share nothing part of this architecture. All of the data obviously resides across all of these compute nodes, hopefully spread evenly out. I'll explain about 15 slides from now how we get data across those compute nodes. Underneath the compute nodes, Redshift typically talks to S3. You're going to typically load data off of S3. You're also going to unload data if you want to remove data from your cluster because you want to do something else with it. Behind the scenes, we're constantly backing data up in Redshift. It's a fully managed service. So the data, there's these automatic backups, and we're always flushing that data to S3. You can also, if you wanted to, restore a cluster or spin up an entirely new cluster based on the backup. About 2 years ago, we released a feature to Redshift that we call Amazon Redshift Spectrum. Spectrum is this extra layer of compute nodes that sits between your cluster and S3 and allows you to query S3 directly. So think of this like external tables where the data resides on S3 and you can execute queries directly against it. Some of our customers also use this Spectrum functionality to load data through it as well. So it's basically for querying and loading data. So the first piece of terminology I'm going to introduce you to is columnar. It's pretty simple. It's really just storing the data on disk column by column. And the reason Redshift uses this architecture is because when you're running analytics queries, we're typically going to be reading many rows only across a subset of your columns. So you're going to be aggregating maybe millions, if not billions of records. And you're just going to do that across maybe a fraction of the number of columns in your table. Just to illustrate this, say if we have this really simple example, I have this simple 3-column table, this deep dive table, some data in it. And if I wanted to just execute this very simple SQL query, I'm just selecting the minimum date here, in a row-based database, assuming I don't have an index to help out, I would end up having to read all of the data off disk in this table in order to find that minimum date, because you have to read each row, go to seek to the column you're looking for, extract that value, and figure out what the min is. In Redshift, on the other hand, we can just scan down that single column. So we can just read, we only need to read the date column off disk. And that's one of the ways that Redshift reduces the amount of I/O that needs to be done when executing queries. So the next piece of terminology, compression. Compression is largely handled for you now in Redshift. Basically, the first time you load data in, you end up getting some compression settings applied to your tables. That's automatic. You can always apply compression manually to Redshift as well. We have a command built in called analyze compression that will analyze all of the data in your table, or a subset of it actually. And what it'll do is it'll pick it up, it'll compress it with every one of our encoding types, and it'll give you back the smallest, what's going to result in the smallest amount of data on disk. We usually recommend compression pretty much on every table. It has two benefits. One, it allows you to store more data in your cluster. And the second benefit is it actually improves performance because we're reducing I/O. So just as an example of how compression works in Redshift, we have our deep dive table up there. You can manually apply compression settings there. So with the encode statement, which you can see that I've written up there. The other important thing is that the encoding is column by column in Redshift. So different columns can have different compression types. And that means each column can grow and shrink independently. So our best practices on compression, basically apply it or attempt to apply it to every table. If the analyze compression command ends up spitting out raw as the recommendation, it's probably because the table is really small and it doesn't benefit from compression, or maybe that column contains mostly nulls. Sometimes the sparse columns will end up coming back with raw as well. I have a little bit of SQL written out here that I added. That's where you get one of the system tables where you can find the compression that's applied to an existing table. Next piece of terminology, blocks. Our blocks are really big in Redshift. They're 1 meg blocks. Every block is encoded with one of 12 different encoding types, one of those encoding types being raw. When we apply compression to Redshift, you can technically have millions of values within a single block. Usually I'll see 250,000 values or so if I were to look in the system table and see how many values are in there. But if you're getting really good compression, yeah, you definitely squeeze over 1 million values in a single block. So the next piece of terminology, zone maps. This is really just metadata about the blocks. The important piece of metadata in here is the minimum and maximum values. So Redshift automatically stores the min and max value for every single block in the entire system. We use that information to reduce I/O, and I'll illustrate how that works in about 3 slides from now. The next piece of terminology is data sorting. Data sorting is the actual physical sort of the data on disk. And the primary purpose of sorting data is to leverage the zone maps or make them more effective. So the zone maps I was talking about on the last slide, we sort data to make the zone maps more effective. Just to illustrate sorting, this is very simple. We have same table, those rows. You can see I'm going to manually add the sort key there so that you see the date location. That's how I would sort this table by those. And if I were to sort that, it's first going to sort by the date, and then it's going to sort by the location. So a very simple concept, just physically sorting the data by those 2 columns. Now tying this together, the zone maps and the sort keys, say if I have these 4 blocks on disk and I have the zone maps printed out beside each of the blocks there, so the min and max values. If I were to execute this very simple query, just counting the number of records on a particular day, what Redshift is going to do, it's going to check the zone maps first before reading blocks off disk, and it's going to be able to eliminate some of these blocks. So in this case, we've reduced some I/O. Now, if I were to sort this exact same table by the date, I'm going to end up with the zone maps being in much better shape. You can see that they all run in sequential order now. Now in this case, when I execute the query, I know I only need to read just a single block. So the sorting the tables makes the zone maps more effective and thus reduces I/O. That is the primary purpose of sorting data in Redshift. Our best practices, usually what you're going to do is you're going to add the sort key to the column or columns that you primarily filter on, the predicates and the where clause. Because this is data warehousing, it's almost always going to be the timestamp on your fact table or a date. So And that's because we're usually filtering, or we have some sort of where date between this value and this value. So that's usually the sort key. And if you're not sure what to do, probably just apply it to that. One catch is if you are going to be applying sort keys to multiple columns, as soon as you have a high cardinality value, it doesn't make sense to add additional columns after that. Usually, as a rule of thumb, I find 3 or 4 columns is about the maximum that you also want to sort by. So this one is, I added this slide actually primarily for migrations from legacy systems. This top SQL example, which I'll walk through, is one that I usually see that customers kind of hit when they're doing migrations. So we want to try and put our predicate columns on our fact tables, which means a little bit more denormalization than we may be used to. So one of those is time or date dimension tables, which are very common in data warehousing. In Redshift, ideally we want to denormalize that into our fact table so we can leverage the zone maps on the fact table. So in these middle 2 lines of SQL here, you can see that how I would query that if I had a date dimension table. If I were to take those values, put them in the fact table, and run that second line of SQL, it will run significantly faster than doing that join. Even if we've set the distribution keys and everything up perfectly, that still will run much faster because the zone maps are more effective. The second one kind of applies to all data warehousing. This is basically try and materialize filtered columns. Don't run them through functions and that sort of thing. And while that obviously saves work, the main purpose, again, is we want to have the zone maps on the table so we can leverage those. And that's what that second query will do. So this concept is slices. This next one here is a really important one. It's how we get parallelism within a Redshift cluster. So we divvy up each one of our compute nodes into either 2 or 16 slices. And those slices are where the data resides, and there's a collection of processes that work against the data on each of the slices. So I'm going to kind of explain how we spread data out across a Redshift cluster. We have 3 mechanisms, sort of 4 now, with our new dist style auto, which I'll talk a little bit about. The first is distribution style key. And what key does is you pick one of the columns in the table to distribute by. And what we do is for each row, we take the value, we hash it. That hash will correspond to one of the slices in the cluster. And the entire row then goes to that slice. So that's dist style key. The next is dist style even. And what even does is, maybe if you don't have a good key to distribute on, it's like just saying, Redshift, please just distribute this data evenly for me. And we just round robin the data through the cluster. So that was the way that I used to recommend customers to use dist style even. I'll talk about auto after I'm done with all. All is a special case, sort of. It's meant for small tables, dimension tables primarily. And what it does is it makes a complete copy of the table on each node in the cluster. So primarily small tables. Our rule of thumb is usually 3 million records or less for dist style all. What auto does, and it's the new default in Redshift, we released it last December. What it does is it basically will switch automatically between all and even today. So if you use dist style auto, which is the default, and you have, say, like a few thousand rows, that table will be dist style all. You continue to add data to that table, and it passes a threshold, it will flip to dist style even automatically in the background. So that's the new distribution style, which is our new default. So I'm going to walk you through even, key, and all, and explain how these work. So let's just say the same table we've been working with. We have 4 records here, and I want to just distribute these records with dist style even. I got this very simple insert statement here. With even, the records are just going to evenly spread across the slices in the cluster here. We have 2 compute nodes, and we have 4 slices. So a very simple example. Now let's try dist style key. In this particular example, what I've done is you can see the DDL syntax here. I picked the location column. There's SFO and JFK, SFO, JFK, those 4 records there. What I'm gonna do is I'm gonna take that first SFO and it's gonna get hashed, and maybe it corresponds to slice 0 here. JFK, maybe it happens to hash out to slice 1. JFK is gonna go back to slice 0, and SFO, obviously the same location. This is an example of a bad distribution key in Redshift. If I were to execute a SQL query against this data, what would end up happening is obviously node number 2 there has no data, it can't do any work. So that's not what we wanna have happen. We wanna have something that looks more like what happened when we use diststyle even. So I'm gonna pick instead the audience ID there. And obviously the value is 1, 2, 3, 4, very high cardinality. We have, looks like it's a primary key or something like that. So in this particular case, 1 might hash there, 2 might hash over to slice 2, maybe that value goes there and the 4th one goes there. Obviously I made the example with 4 rows work perfectly, but if you have a large number of records, we're talking millions of records, statistically the data is going to end up evenly spread across the cluster. So that's diststyle key. Diststyle all, on the other hand, what this distribution style does is, again, we make a complete copy on each node in the cluster. And what we do as each row comes in is we write it actually to the first slice on each node. So that's how diststyle all works. This is again for optimizing small tables and making joins with them more efficient. So just to recap, diststyle key. We use this with joins. So the idea here is if I have 2 really large tables, we want to co-locate the rows that we're joining onto the same slice. So with the on clause in your SQL, where you have that on and those 2 columns that you're going to be doing the join on, if both of those are the disk keys, that will make the join significantly faster. Now, one catch is we don't want to cause skew of the data. So I have the SQL query written up here. That is where you can see if there is skew happening with that table. What that ratio is it's the ratio between the slice with the most amount of data and the slice with the least amount of data. And ideally, it should be close to 1.0. My recommendation is a maximum of around 1.4, maybe 1.5 would be an absolute max. Think of it like a skew of 2. That would mean there'd be twice as much data on one slice as another. Diststyle all, my rule of thumb is 3 million rows or less. It's usually safe to use diststyle all as long as you're not doing a large number of writes to that table. Diststyle even, I probably wouldn't use that anymore unless you know for sure that the table's going to end up being or needing to be diststyle even. The new default diststyle auto does a great job. Like I said, it flips back and forth or between all and even. We have it set fairly low right now. It's just 80K records. We've been changing that value behind the scenes as we get more data. We're being cautious obviously with it, but if you know that you have a dimension table and it is under 3 million, you can still safely use diststyle all. So just a handful of, this is mostly summarization here of what I've already talked about. Obviously add compression to your tables, add a sort key to the columns that you primarily filter on. I talked about the materializing values into your fact table. Just because I've seen it happen quite a few times, avoid distribution keys on time-based things. Some customers that will apply it to a date, seems like it should work. You check the skew and you get nice even distribution of data. And then you run a query that maybe only is running on a single day. And all of that day's data resides on a single slice, and it ends up causing what we call in-flight skew. So that's just, as a rule of thumb, I usually say don't add it on temporal columns. The last one here, not really a summary item. Varchars, chars, try and keep them as narrow as they need to be. You don't have to go crazy with this. It just uses a little bit more memory when we execute queries if they're declared really long. So as an example, don't do varchar 1024 on a state abbreviation, for example. It's just wasteful. If you make it varchar 10 or something like that, totally fine. So let's go into data storage. So we don't really advertise this one in our docs or anything like that, but the compute nodes are significantly larger than what we advertise. We have a lot more storage on them. And the reason we do that is the space we advertise is what you actually get for your data. We mirror all the data in the cluster, so when you write data to one node, it gets written to another node in the cluster. We obviously have an operating system on Redshift. There's temp and all of that kind of stuff carved aside. So that's why the compute nodes have a lot more space than what we say. Once the data is committed, like I said, it is on 2 nodes in the cluster. We also asynchronously then back that data up to S3. So every 5 gigs of change data, which is actually a very small amount of data in Redshift, or 8 hours, whichever happens first, that will trigger the flush to S3. One exception to this is temporary tables, and I like to call this one out because you can write data to them significantly faster. So if you're needing staging tables, things like that, or things that really are temporary in nature, definitely leverage temp tables because they write way faster. So Redshift is an ACID compliant. It is fully transactionable. We really only have one isolation level in Redshift though. It's serializable. You can request the other ones. You'll just end up getting a serializable isolation level. Our commits there's 2 phases to them. Obviously it's an MPP data warehouse. We have many nodes. So there's a local phase to the commit and a global phase. Because of that, commits are more expensive in Redshift than they are in say a regular just database with SMP database. One thing that customers also don't realize is that the DDL is transactionable in Redshift. So you can actually begin a transaction, do DDL, and roll it back. If you don't declare a transaction though, what will end up happening is Redshift, if you have auto commit on, will end up doing 1 transaction for every DDL statement. That can get expensive if there's a large number of transactions. So what we usually will recommend, and you probably want this for correctness anyways, is to wrap workflows in an explicit transaction. Okay? The copy statement in Redshift is the primary way of ingesting data. I'm going to walk you through kind of how it works. Let's just say we have one of these compute nodes. This is our DC2 8XL compute node. It has 16 slices. It's one of the bigger ones. And say we have a single file here on disk. If you were to issue, or that file will say is on S3, if you were to issue a copy statement against this cluster, what's going to end up happening is Redshift's going to look at S3, it's going to go, okay, I got one file, and it's going to have, in this case, the slice 0 is going to reach out, pull that file up, it's going to stream it, it's going to parse it, and it's going to distribute the data across all the slices. It's not really that efficient. If we wanted to get some parallelism out of this and we broke that same file up into 16 chunks because we have 16 slices, now what's going to happen is every one of the slices in the cluster is going to reach out in parallel to S3 and it's going to pull that file up. And then it's going to parse it, distribute it, and get it written to disk. And this actually scales linearly. So you'll get a very close to a 16x performance improvement by splitting the files. Our rule of thumb, 1 meg files to 1 gig, somewhere in that range after you apply gzip compression. We do now have Z standard compression. I haven't actually tried that out, but I'll just kind of throw it out. It has a higher compression rate than gzip and is also technically faster to decompress. I don't have numbers on it. It's just a brand new thing that we just released. So as a rule, these are kind of some things that I've encountered when helping customers work through actually mostly migrations from other systems. Pick a simple delimiter if you're using CSV files, which is what most customers use. Don't try and use crazy unprintable characters, picking bells or UTF-8 characters. Just pick something simple like a pipe or a comma. You can escape everything that you need to, wrap strings in double quotes and that sort of thing. Pick a simple null character. Usually, \N works well. I've seen some customers for some reason use \n, that means a new line, and that doesn't work. So again, just pick simple stuff. One thing I'll call out is UTF-8 characters. They take up 4 bytes in Redshift, and when you declare a varchar, that actually is the length in bytes. So if you are going to be storing UTF-8 characters, you'll have to extend the length of your varchars to compensate. Redshift Spectrum, I mentioned when we were kind of covering the architecture that customers use this for ingesting data. One nice thing about this is, especially if you have Parquet data on S3 and you only want to ingest a subset of the columns, that's actually a great way to ingest data. So you can do an insert into with a select statement, and that select can do all sorts of things. You could select only some of the columns, you can filter data because you can put a where clause, you can aggregate data as it's coming in. So it gives a lot of flexibility, a lot more flexibility in the copy statement. So if you're wanting to do some sort of transformations or filtering, definitely leverage Spectrum for that. Redshift is designed for big data. It is a batch processing. It primarily does batch processing. So because of that, a small write in Redshift, because of our large blocks, is actually just as expensive as writing a large amount of data. So micro batching is completely fine in Redshift. A lot of customers will do like 1 minute micro batch increments, which is fine. But just be aware of that. If single row inserts, for example, isn't something you want to do in Redshift. You want to leverage the copy statement and bulk load. Updates and deletes, I'll cover deletes. When you delete data in Redshift, we actually just tag records for deletion. We don't actually remove it right away. Updates, what updates do is they'll tag the record for deletion and they'll add a new record to the end of the table. Okay? Redshift uses multi-version concurrency control, so that's the reason it works like that. We do need to clean those up. Auto vacuum is in Redshift for deletes, and so the auto vacuum system will clean up the deleted records. This is a very frequent question I have on how to do basically merging of data or upserts, especially when migrations are in flight and you have some existing logic. So I'll kind of walk through. This is the same deep dive table, same 4 rows. And let's just say we have some CSV file. The CSV file is on S3 and you're loading that file. And in this file, we find we want to update 2 records, just changing a couple values. And we're going to add 2 new records in the CSV file. So how do we do that? The copy statement is append only, so we have to kind of work around this. The workflow is to load that data into a staging table. Then what we want to do is we want to delete the data out of the production table that matches and then insert all of the data over from our staging table into our prod table. So I mentioned the transactions and wrapping things in a transaction. So I'm going to start out with a begin statement, create a new transaction. Then I'm going to create a temporary table. So the reason why is, remember, temporary tables twice as fast. Then I'm going to use this like keyword, and I'm going to copy over all of the settings from the previous deep dive table. So this is going to copy over the compression settings. It's also going to copy over the distribution key. When we insert data from one table to another, they have the same distribution key. It's going to be a faster copy of data. I'm going to use the copy statement here. I've turned off compression or analyzing compression automatically because we've already set it with the like command. Then what I'm going to do is I'm going to execute this delete statement. I'm going to delete all the data out of my prod table where the IDs match, but that's okay. Everyone else is not going to see this because this is all in a transaction. Then I'm going to insert the records over. I can drop my staging table safely now. And now I can finish the transaction and everyone gets a consistent view of the data, even if they were querying it while this workflow was happening. So just to summarize and wrap this up here, I mentioned wrapping things in an explicit transaction. Consider using drop table or truncate instead of delete. That's just in case, that's instead of doing, say we wouldn't want to delete data out of that staging table. It's just more work for vacuum. If we were to drop it, as the data is just gone, no vacuum necessary. If we are trying to use temporary tables, if you have to use a permanent table, you can also consider using the backup no option. What that does is it says, hey, don't flush that table to S3. Make sure both the staging and the prod table have the same distribution key if they can. The reason for that is that insert into with a select will be much faster because they're both tables data resides on the same slice. The comp update one is basically we don't want to be figuring out compression repeatedly over and over again on those staging tables if you're creating them and dropping them without compression. But that like keyword that I used, that'll take care of that. And the last one there, this alter table append, it's a little bit, if you've used swap partition, it's a little bit like that command. A lot of times I don't talk about this one, but it is, if you're going to have a staging table with probably more like hundreds of millions, if not billions of records, and you want to quickly move that data to another table, it'll be almost instant. It's like a DDL command. And what it does is it basically rewrites the metadata so that table's data now belongs to another table. It's a very powerful command, but yeah, only use it if you're going to be needing to move very large portions of data. If you're not, just stick to the insert into with a select. So vacuum and analyze, I've kind of mentioned them a little bit. Vacuum, delete. We now have auto vacuum for deletes. We also have auto analyze. So what vacuum does two things. It removes the deleted records, and it also resorts the table, so the table is globally sorted. The delete portion of it is fully automated now. It's not something you need to worry about. Analyze is for collecting statistics on tables. So this is where it samples a table, figures out things like cardinality and stuff. That has also been automated. So again, not something you need to worry about. So those two completely done. Vacuum sort, unfortunately, you still need to schedule that. Most customers run it like once a day, maybe once a week if you're mostly loading data in sorted order. So you unfortunately do need to do the vacuum sort. We have announced though that actually is coming. It was announced at reInvent, so we are still continuing to work on auto vacuum sort. So WLM, workload management. The purpose of workload management is to separate different types of query workloads and isolating the resources for them. So a lot of times we have different competing workloads that run on a cluster, and some of them might be more important to us than others. For example, we usually want to prioritize dashboards, maybe our Tableau queries, that sort of thing. And the ETL or the ingestion of data is maybe less important. So we might separate those two concerns. So how we do this in Redshift is we can create what are called queues. Every single query in a Redshift cluster executes in a queue. By default, sort of by default now, I'll talk a little bit about auto WLM in a couple slides. By default, we have a single queue with 5 slots. That's kind of, so you can throw 5 queries at Redshift, and after that, they will queue. A lot of customers set up WLM, expand it beyond that. Most customers will set up to run somewhere between 12 and 15 queries is typically what they'll set up. And then they'll enable this feature that we call SQA, or short query acceleration. What SQA does is it analyzes incoming queries. If the queue is full, what we do is it will look at the query and say, we know we can run this in a couple seconds. We will immediately run it anyways, even though your main queue is full. So it kind of gets hopped into a different, into the short query queue, which is kind of a hidden off. And the idea here is, if you have short running queries that only take like a second or two to run, we just want to get them out of the system, make the end user feel like things are fairly snappy still. If we're slowing up long running queries that take minutes or hours to run, and they take a few extra minutes, it's probably not a big deal. So the idea is keep short running queries running quickly. So each one of our queues in Redshift is split up into something that we call slots. It corresponds to the concurrency in the system, and each one of these slots has a certain amount of memory that is assigned to it. Concurrency scaling, what this is this was a feature that we recently released at the end of March, and what it does is if a queue is full, we can spin up additional Redshift clusters and send the queries over to those additional clusters and leverage the backup. And I'll talk about that quite a bit more in depth in a few slides. So the first thing here, I'm going to walk through just an example of how a typical customer sets up workload management. I've created this scenario that is very generic. Light ingestion, peak reporting, during the middle of the day, and then a heavy ingestion overnight, and just your typical spread of types of users. And in this scenario, if I were to set up a WLM queue, I would probably set it up something like this. I'd have an ingestion queue. I'd keep a fairly low number of slots on that ingestion queue, a reasonable amount of memory per slot. So I've configured it with 20% memory, 2 concurrency. That means each slot has 10% of the cluster's memory. My dashboard there, I'm going to give it quite a larger number of concurrency. So I've set it up to 10 or 10 slots, and I've enabled concurrency scaling, which allows it to leverage additional Redshift clusters. Then I have this default queue here at the end. We'll say that's kind of like my queue for everyone else, maybe my data science users, business analysts that are going to run ad hoc queries. And I've set the concurrency or the number of slots on this quite a bit lower. I've also allowed them to use concurrency scaling as well. I'm assuming these guys are going to be running more beefy queries than what the dashboard is, so that's why they have like 8% memory each. One thing that I've kind of done here is this it's hidden the super user queue. So we do have in Redshift, it's not really meant to be hidden, it just doesn't show up in the console, it's in the documentation. There is an additional queue in Redshift that we call the super user queue. That queue, any super user can switch to that and use it. It's meant for administration tasks. So if say someone, you just wanted to do some administrative work, maybe dropping some tables, things like that, you can definitely leverage that queue. You probably don't want to be using it for executing long-running queries or things like that though. So concurrency scaling, I mentioned I would talk about how this works. So say we have our single cluster here and we start sending a ton of queries to this thing and the queues start filling up. What we end up doing is we flush the data to S3 out of the cluster, so our backup there, and we end up spinning up an additional Redshift cluster. That additional Redshift cluster, instead of having the queries queuing and waiting on the main cluster, we instead send it over to the other cluster. It needs to hit S3 to pull that data and start pulling that data off of S3. But what we found is for a lot of queries, it's beneficial to use this second cluster. It's faster than waiting, for your turn to run. And so we end up alleviating the load on the main cluster and getting that query running immediately. Now, if say more queries continue to come in, we can also spin up even more clusters. By default, we allow up to 10 additional Redshift clusters to be spun up. You can select and limit the number of it when you enable concurrency scaling. So that's done per queue in the WLM section to enable it. We did a lot of analysis on the fleet and seeing how many customers were going to benefit from this. One thing that we did is for every 24 hours that your cluster runs, your main cluster, we give you 1 hour of free concurrency scaling. We found that 97% of our customers, if they were to enable concurrency scaling, this feature would be free for them. So we wanted to make this feature mostly free. So I'm going to talk briefly about QMR. QMR was a feature that we added for those of you that have people that use Redshift that you wish weren't connected to your Redshift cluster. These are customers that maybe write Cartesian joins and just do bad stuff, try and drag 1 billion records out of the cluster. What QMR does is it allows you to write rules to detect these poorly written queries and abort them automatically. So this way, someone's not getting paged and needing to find the bad query and killing it manually. That was the primary purpose for this feature. Another portion of it, though, is you can also log the queries. I highly recommend that, logging long-running queries in Redshift. So that's one rule I always just recommend. Just set up a rule, and log your long-running ones. So just to recap the best practices for WLM, keep the number of queues you have to a minimum. Don't try and set up like 6 queues, things like that. What ends up happening is you don't use them all. Use WLM to limit your ingestion. Usually to 2 or 3 is a good rule of thumb. Keep your WLM limited to about 15. And I mentioned the long-running queries already and usage of the super user queue. So jumping quickly into cluster sizing, we have 2 instance types in Redshift. Our DC2, which is SSD, and DS2, which is magnetic disk. Basically, the SSDs are obviously faster. They do cost more. And each of these instance types comes in 2 different sizes. We have a smaller instance and an 8XL, which is the big instance type. You can see the information about it up there. So when sizing an Amazon Redshift cluster, I always recommend starting with how much uncompressed data you have in your legacy system. Assume you're going to get a 3 times compression ratio in Redshift. It's probably going to end up being closer to 4 times, but I think 3 is just it's a good rule of thumb to start out with. And target having around 30 to 40% free disk space. We usually always recommend keeping it under 80% as the red line. And then pick HDD or SSD depending on what kind of performance you require. Usually some of our, if you're coming from a high performing legacy system, you obviously want to pick the SSDs. So just as an example of how I would do this at work, if a customer came to me and said, I have 20 terabytes of data in my legacy system, I would take that and assume it's about 6.7 terabytes. Then depending on the performance requirements, I would either pick 4 of our DC2 8XLs or 5 of our DS2 extra large, which would give you 10 terabytes of capacity and enough free space to do work. So that's how I would do that sizing. Now, there's 2 ways, if you get it wrong, to resize a Redshift cluster. There's our classic and there's what we call elastic resize. Our classic resize, what it does is, say if we have these 3 compute nodes here, we want to resize this to 4. We spin up an entirely new cluster in the background. We then drop the main cluster in read-only. We do a binary stream of the data over. Once the data is fully streamed over, we redirect the DNS and we bounce the connections and you're up and running on the new cluster. Now how we do the new elastic resize, say if we have the same 3 nodes and we want to incrementally add one, we just want to add some storage maybe. What we do is when you click the button to resize this, it quite literally is just a type a new number and click, we spin up or we attach an extra node to this cluster, we kick off the backup to S3. This usually takes around 10-ish minutes or so. Once it's complete, what ends up happening is we basically redistribute the metadata, and this portion of it takes around 4 minutes. It's actually really fast. As we redistribute the metadata, we hold all the queries. So all in-flight queries are put on pause, and once that step is done, we begin to restore the data, and the cluster is fully available now at this point for both reads and for writes. So you get about a 4-minute-ish outage where you can't do reads or writes in this step. So where you would pick one, or this is actually, there is some limitations with it on the small instance types. With the small ones, you can only either double or cut in half because there's just not enough slices to work with. We're redistributing metadata on the nodes. On our 8XLs, however, because we have so many slices, we can incrementally add nodes. So if say we started with a 4-node cluster, I could incrementally go 5, 6, 7, 8, or all the way down to 2. So all the way up to doubling and all the way to in half. So when you would use one versus the other, you would use elastic resize, maybe scaling up for spiky write workloads, incrementally just adding and removing storage. The classic one, you can switch hardware types. So if you started out on magnetic disks and you wanted to move to SSDs, classic resize allows you to switch instance types as well. Obviously, if the limitations of elastic resize are restricting you, you would obviously also use classic resize. And you can see the difference in the amount of time it takes while the cluster is kind of doing these. The classic resize, usually an overnight operation. So with cluster sizing, the one thing that I always say, if you're doing a prod workload, make sure you have 2 nodes or more. And the reason why is you want the redundancy from the mirrored copy. Maintain at least 20% minimum space. And if you happen to be a customer using DC1s, migrate off of those. We'll allow you to even migrate your reserved instances. We don't want you running those at all, really. We want you to have the best experience with Redshift. The DC2s, in a lot of cases, are 2 times faster, so it's a free migration. Now, just to hit the summary here, I kind of put this together to summarize those of you who are looking for legacy, moving from legacy systems. The row-based data, if you're coming from a row-based database, which many people are, denormalize further. Remember, don't use those date dimension tables. Get whatever you're going to be filtering on, the predicates, into your fact table. Redshift is columnar. It does well with really wide fact tables. I have customers that run like 300 plus columns on a single table, and that's fine. If you're coming from an SMP system, you do have to think about distribution keys. It's not something you have to think about in SMP. So if you have those, an SMP system, you will need to co-locate data for your large joins. So that's really the one thing you have to kind of think about that's different. Redshift, like I mentioned before in the very beginning, it is meant for big data. If we're talking like, 10, 20 gigs of data, it might make more sense to use RDS or Aurora, Postgres. And then when you reach sufficient size, the switch over to Redshift is really easy because the SQL syntax is almost the exact same. We also added stored procedures. A lot of people don't realize that we put this in. It was only launched last month. We have PLPG SQL, which is the Postgres language, stored procs now in Redshift. And we added that for those of you who are doing migrations, making them easier. So just some additional resources. We have a bunch of links here on GitHub. There are some scripts and things that we find customers find useful. Check those out. We also have a handful of blogs here. The top one is really great. It's the design playbook, top 10 performance tuning. That is a great blog as well. So just extra tips and tricks. Thank you guys very much.